Okay, so I think what we covered this morning was great for setting the stage. Adam earlier said that he was not going to tell you which frequentist or Bayesian method to take in a given problem. And this lecture is going to be all about like why you should use the Bayesian approach. Again, there are certain problems where being a frequentist is a great choice, and there are certain situations where you would mix the two. But here we will see why Bayesian inference is awesome. Okay, so just going to start off with Bayes' theorem, which we saw alluded to this morning. Can people see this? Great. Okay, so Bayes' theorem allows us to write down the conditional probability of some hypothesis A given the observation of some data B. And if we know the probability of the observation, given that we've assumed that the hypothesis A is true, and some initial guess for the probability of hypothesis A, and some overall probability of the observation B. So all of these components of Bayes' theorem have specific names. This is the likelihood. This is the prior. This is the evidence. And this is the posterior. So Adam already mentioned this morning that the likelihood is not necessarily a probability distribution. And so in this case, the prior does have to be a properly normalized probability distribution, as does the posterior. And so sometimes the evidence is also called the marginalized likelihood. Which basically means that it's a normalization constant for the numerator here. Okay, so this might seem a little bit esoteric, and so let's see how this actually works in action. So let's consider an example problem in the context of outdoor dining, because it's that time of year. So our favorite restaurant has opened up their patio for the season, and we know that if it's sunny, there's a 75% chance that the patio is going to be open. So the probability that the patio is open if it's sunny is 0.7. So it might be closed for private events, or there might not be enough staff, and so it's not always open if it's sunny. We also know that if it's raining, there's a 0% chance that the patio is open because no one wants to get soggy while they're dining al fresco. Okay, and let's say in our part of the world where we live, where our favorite restaurant is, the probability that it's sunny on a given day is 60%. Okay, so now we want to calculate the probability of it being sunny if we know that the patio is open. So again, this is the notation of conditional probability. So this is the conditional bar, which means that whatever's on the left-hand side of the conditional bar depends on whatever's on the right-hand side of the conditional bar. Okay, so who can tell me, let's start like putting this together, right? So we want this thing. So which, like, let's use Bayes' theorem and basically fill out what the right-hand side of this equation should be. Going to put this over here, but we'll leave this up so we have it for context. So if we want P of sun given patio, what is the likelihood? Yes. Yes. Okay, and what's the prior? Yeah. Awesome. And then the evidence is just P of patio. Okay, so how do we calculate these things? One of these we already have, P of patio given sun, that was given to us. Great. We also have the prior, P of sun is 0.6. Okay, so that means that we need to calculate the evidence. So again, the evidence is the marginal likelihood. So it's basically the likelihood summed over all possible prior probabilities. So it would be P patio given sun, E of sun, plus P of patio given rain, P of rain. Okay, so we weren't given P of rain, but if we assume that there are only two possible outcomes, sun and rain, what is P of rain? Great. Okay, and so then our evidence is just going to be 0.45. You can take my word for it. Okay, we can also go back and calculate P of no patio, which we can leave as an exercise to the reader. But again, because there are only two outcomes, you can kind of deduce what it would be. Okay, so now we have all of the elements of our statement of Bayes' theorem. So this is just 0.75 times 0.6 divided by 4. And this means that the probability of sun given patio, I did not write this down. Y'all can plug this into your calculator. And so we could go through and calculate the other four possibilities as well, right? So we can also calculate the probability that it's sunny given that the patio is closed, and the probability that it's raining given the patio is closed, and on and on. So this is just a simple example to kind of get you familiar with the various components of Bayes' theorem and how we calculate them. So I think what's really crucial here is basically how we calculated the evidence. So we summed over all the possible outcomes in order to get the marginalized likelihood P of patio. Yes. Yes. Exactly. Exactly. Yes. So I think probably the more interesting question to calculate is what is the probability of it being sunny if the patio is closed? And then it would not be 1, but yes, in this case, it's 1. Okay, so this is one example. But now we kind of want to think about this more generally, and we want to compare the frequentist and the Bayesian approaches. So we're going to start in the context of a specific problem, and we're going to pretend that we're taking a statistics class, and we want to know whether it's useful to read the textbook for this class. And we can get some estimate of how useful the textbook is going to be based on the results of previous iterations of students that have taken this class. So we're going to approach this problem from both the frequentist and the Bayesian methods. So let's start with the frequentist approach. So for the frequentist approach, we already saw this morning that frequentists calculate probabilities based on like repeated trials of an experiment. And then basically the probability is just going to be basically if you take the number of trials in the experiment to infinity. So write this mathematically. if you want some outcome A of your experiment in your frequentist approach to calculating the probability of getting this outcome, you would do in an ideal world, infinite number of trials of this experiment, and then you would just count how many times did you get the outcome A. Okay, so in our hypothetical statistics class, in the previous year, we had a class of 40 students, and half read the textbook and half didn't read the textbook. And for the purposes of this problem, we're going to assume that whether or not the student read the textbook was the only thing that was different in their preparation for the exam. Okay, so of the half that did pass, that did read the textbook, we see that 16 out of 20 passed the exam, while for the half that did not read the textbook, only 4 out of 20 passed the exam. And so we can kind of get a sense from these numbers that probably reading the textbook is going to help you pass the exam, but let's calculate this rigorously. Okay, so since we have an equal number of students that did and did not read the textbook, we can simplify this and just focus on the students that passed the exam. Yes.
So, like, conceptually, there's always this concept of like null hypothesis. Like,
Yes.
and this is what never made sense to me. Like, why are we trying to disprove the wrong assumption instead of the much more simple, conceptually step of proving the correct?
I think it's two sides of the same coin. Like, I think it's kind of like philosophical which one you want to do. In this case, our null hypothesis is that reading the textbook does not affect whether or not you're going to pass the exam. And for this problem, we're going to see that it's pretty straightforward to prove this one hypothesis wrong. Whereas you could also phrase it in terms of the hypothesis is that the reading the textbook does help you pass the exam, but for the formulation of this problem, that becomes a little bit more conceptually difficult, but they are basically equivalent ways of approaching the same problem. Yeah. Okay, so right, we've said that we want to rule out this hypothesis that reading the textbook does not help you pass the exam. And so basically we need to come up with a statistical model for our experiment. So there are two possible outcomes in the group of students that did pass the exam. Either they did or did not read the textbook. And since there are only two possible outcomes, this is a Bernoulli process. And if you repeat a Bernoulli process n times, the resulting distribution on the number of successes in your process is given by a binomial distribution. So another example of a Bernoulli process is just a coin flip experiment. And the same thing would apply here if you wanted to calculate the probability of getting, heads 4 times out of flipping a coin 20 times. And so the various components of this binomial distribution. So K is the number of successes. So in our case, how you define K is flexible. And so for the first iteration of this, we're going to assume that a success is just that the student did not read the textbook. So it's not necessarily pass or fail. It's whatever you want to be considered the good outcome of the experiment. And in this case, N is 20 because we have 20 students that pass the exam. And then P is the probability of having read the textbook in the group of students that pass the exam. So if reading the textbook has no bearing on whether or not you pass the exam, then P should be 0.5. For a given set of students, it would be equally likely that a student who passed the exam would or would not have read the textbook. So this is our null hypothesis. Okay. So we can look at the expected number of students who did not read the textbook but passed the exam, given our Bernoulli distribution. And if the probability is 0.5, then we would expect that half of the students who passed the exam did not read the textbook and the other half did. But what we actually measure is that 4 students did not read the textbook and 16 did. And so this is just if I basically calculate this Bernoulli distribution as a function of k, this is what I get. It peaks at 10, and that's what we expect given a probability of 0.5. And the way that I've done this is I'm using SciPy, which is going to be super helpful for all the rest of the tutorials in this session. And you can see that I'm calling a method called the PMF, which is the probability mass function, and it's just a discrete probability density function. So because the binomial distribution is a function of discrete parameters, so k can only take on integer values. You can only have an integer number of successes. We don't have a probability density function. We have a probability mass function. Okay, so we saw that k equals 10 is the expected value for the null hypothesis, but we measured k equals 4. And so in the frequentist way of ruling out the null hypothesis, we want to calculate what's called a p-value to quantify how likely it is to obtain an outcome that is at least as extreme as the one that we obtained. So given that we would, on average, expect Bernoulli process repeated 20 times to result in k equals 10, how likely or unlikely is it that we actually measured k equals 4? So in order to do this, we can basically write down exactly what our p-value would be. Okay, so in this case, it is probability of observing 4 or fewer successes out of 20 trials with a probability of success being 0.5. And so since it's 4 or fewer, we sum the values of the binomial distribution for k equals 0, 1, 2, 3, or 4. And this means that these outcomes are at least as extreme as the one we observed. And so when we calculate this p-value and then take its inverse, we obtain 169. So basically this means that I would have to do this experiment with 20 trials 169 times in order to get one iteration where only 4 people who passed the test read the textbook. So this is unlikely, right? And so this basically quantifies the probability that is ascribed to our particular outcome. And so we conclude that this is a very unlikely outcome, and actually it's better for us if we read the textbook. And you can also calculate it the other way, right? So now you want to say, well, what's the probability that 16 or more students who pass the exam read the textbook? If you calculate it that way, so replacing 0 and 4 here with 16 and 20, then you get the same thing. Okay, so we've calculated our frequentist p-value and determined that actually reading the textbook is better for your ability to pass the exam for this class. Okay, so what about the Bayesian approach? And in the Bayesian approach, first we're going to constrain p. So instead of assuming that p equals 0.5, which was our null hypothesis in the frequentist sense, we're going to measure p given our observation that k equals 16, the number of students who passed the exam and read the textbook was 16. Okay, so we're going to build this step by step. We're first going to assume a uniform prior, and we're not really going to talk about how to choose priors because you're going to have a whole session about that tomorrow, I think. Okay, so we're going to assume a uniform prior. P is the probability of having read the textbook if you pass the exam, and so it must be between 0 and 1. Okay, next we need our likelihood. So again, the likelihood is P of our observation or our data given our model. And so we've observed 16 students having read the textbook out of the ones that passed the exam, 20. And so now you can see that we've kind of flipped what we are plugging into our binomial distribution. So now P is a free parameter and the frequentist approach, K was a free parameter. And so we can, make it on our grid of P's, we can calculate this likelihood. Again, we're using SciPy because it's super convenient. And finally, we need to put together our likelihood and our prior to calculate our posterior. And we just multiply those. And what do we get? So this is our unnormalized, as you can see, posterior on the probability of having read the textbook if you pass the exam. And you can see that it's unnormalized because this is our prior, it integrates to 1, but our posterior very much does not integrate to 1. And this goes back to what Adam was saying earlier. The likelihood is actually a really small value, and so you need to normalize it in order to get a properly normalized probability distribution for your posterior. So let's calculate the evidence and normalize our likelihood. And because we don't necessarily know how to analytically integrate this, might be possible, but we are data scientists, and so we're going to do it numerically. So we numerically integrate our posterior, and this is just our evidence. And so now we can replot our normalized posterior distribution, and we can see that the area under the prior and the area under the posterior both integrate to 1. Okay, so looking at this plot, what would you say is the probability of having read the textbook if you pass the exam? Yeah. Yeah, exactly. And this makes sense, right? Because 16 divided by 20 is 0.8. Okay, great. But what is the best fit value of this model that we've used to describe our data? So one approach is to calculate the maximum likelihood. In this case, we're instead going to look at the maximum posterior. Since we're using a flat prior, the two are equivalent, but for the sake of this demonstration, we're going to argue that the maximum posterior is the best fit because we had some prior belief and the posterior allows us to incorporate that. And so we basically just find where on this plot is the posterior maximized. And it turns out that probably because of our finite spacing, it's slightly smaller than 0.8, but it's basically 0.8. Okay, but we are Bayesians, and so we know that there's some uncertainty in our constraint on the fraction of students who read the textbook and passed the exam, right? This isn't a delta function at 0.8, there's some spread here. So how can we quantify that? So we quantify that by calculating a credible interval. And so in order to do that, we need to first introduce the cumulative density function. So the cumulative density function is just defined as the integral of the probability density function from like the minimum value of the parameter of interest up to some given value of the parameter of interest. And so basically what we're doing is we're very slowly calculating the area under this curve. That's all the cumulative density function is. And so if it's properly normalized, which it should be, then the CDF should range from 0 to 1. Okay, and so now we want to calculate the 90% credible interval. You can choose whatever credible interval you want, but a common choice is 90%. And so this is defined as the smallest continuous probability region that includes the maximum posterior value that also includes 90% of the posterior probability. And so there are multiple ways of doing this. One way that we're going to look at first is called the symmetric credible interval. And so this is technically only valid if you have symmetric posterior distributions, but it's often used as a good approximation for distributions that are unimodal or that have a well-defined peak. And so if we calculate our CDF for the probability density function that we had calculated for P, this is what it looks like. So it starts out at 0 at around 0.5, and then it reaches 1 at 1, which makes sense, right? Because the probability is bounded between 0 and 1, and it peaked at around 0.8, so around half of the probability is contained within P less than 0.8. Okay, and so now we're basically going to define the lower bound of the 90% symmetric credible interval as the value of P where the CDF of P is equal to 0.5. So basically wherever this CDF equals 0.5, and then the upper bound is going to be where the CDF equals 0.95. And so between 0.5 and 0.95, we have 0.9% of the probability. Okay, and we can calculate that and plot it, and this is what it looks like. And so we can kind of encapsulate this with some, this allows us to encapsulate our uncertainty. So we would say that the probability of having read the textbook, given that you've passed the exam, is 0.8. It could be between like 0.62 and 0.9 roughly. Okay, but actually this probability distribution is not symmetric. So technically the symmetric credible interval is not a fully accurate approximation for this posterior. And so instead, we can use a different method to calculate the credible interval called the highest posterior density method. And I think the way that I like to think about this is really just visually. So we have some probability distribution for some variable x. And basically what we're going to do is we're going to choose some arbitrary probability cutoff, and then we're going to calculate the area under the curve where the probability exceeds this cutoff. And we want this cutoff to eventually encapsulate 90% of the area. And so basically this is very useful and allows us to get a more accurate representation of the credible interval when, for example, the distribution is highly asymmetric. So if it peaked at the edge, for example, if we were to calculate the symmetric credible interval, we would probably calculate something like this. And so this actually excludes the maximum posterior value by definition, right? Because we need to leave 5% of the probability on both sides. And so we're excluding our maximum posterior value. But instead, with the highest posterior density method, we basically start from the peak value and slowly walk out to lower and lower probability thresholds until we've bounded 90% of our distribution. And so if we do this, you can look at the code later. This is the credible interval that we get shown in red. And so you can see that they're slightly different, which we expected because this isn't a symmetric distribution. They're not super different because it's still, unimodal, and it's, not super heavily tailed on one side, but they are slightly different. And you'll notice that by definition, at the edges of the highest posterior density credible interval in red, the value of the PDF is the same. Yes.
Is there a way to tell that your posterior is just not going to be symmetric?
So it kind of depends on the exact problem, right? I would say that generically no, but usually when you've reached the stage of calculating credible intervals, you've already calculated your posterior, and so you can plot it and basically look. In certain cases, you would expect it to be multimodal if, for example, you have a periodic variable, or you would expect it to peak at the edge if, for some physical reason, your prior on that parameter is sharply bounded. And so in that case, you might already expect it to be asymmetric. But I would say generically, no. Yeah, good question. Okay. So we have, yeah, question.
This might be something for later on. Maybe missing something. But I was kind of curious if there's a way to like quantify, like we chose like a uniform fire. Is there a way for us to incorporate that into our error, or is this like accounting for that?
Yeah, so in the problems, you're going to see what happens if you choose a different prior for this. And so here we chose a uniform prior. Really, this doesn't encapsulate our null hypothesis super well because our null hypothesis was that p equals 0.5. And so originally we had much stronger prior beliefs that p should be 0.5 rather than 0.1 or 0.9 or whatever. And so just for the purposes of this example, we've chosen a uniform prior, but you will see how/if this changes once you use a prior that encodes more of the like prior belief in the null hypothesis that p equals 0.5. Good question. Yeah. Other questions? Okay. All right, so we've calculated our posterior probability distribution on the probability that a student who passed the exam read the textbook. And now we want to go back to our original question, which was, does reading the textbook help you pass the class? And so in order to calculate this from the Bayesian perspective, we basically are just going to integrate the area under the curve with p greater than 0.5, because if p is greater than 0.5, then you are more likely to have read the textbook if you pass the exam. And if we do that, we find that if you basically do the integration, you get 0.996. And so it is overwhelmingly more likely that you have read the textbook if you've passed the exam. This is not exactly equal to our p-value, but it's pretty close. And so we can see that the frequentist and Bayesian methods of solving this problem gave us slightly different quantitative results for like how much better it is for you to read the textbook if you've passed the exam, but qualitatively they've arrived at basically the same conclusion with more or less the same significance. Okay, so before we go on, this was one thing that kind of was confusing to me a lot when I was first learning about statistics and how we quantify the significance of a result. So you've probably heard that the significance of results in physics and astronomy are often quoted in sigmas, and that often we consider 5 sigma to be the threshold for a significant detection for something. Maybe this is the case more in particle physics, but once you've measured something with 5 sigma significance, this is like smoking gun evidence and a very significant measurement of whatever you're trying to measure. So how do we turn our p-value into a sigma? Basically, the number of sigmas just refers to the number of standard deviations of a Gaussian that encompass the probability density given by 1 minus your p-value. And so our p-value was initially 1 on 169, which is like 0.998 or something. And so we want to calculate for a Gaussian distribution, how wide in our Gaussian do we need to go in order to encapsulate 0.998 of our probability. And so the easiest way to do this is using the inverse of the CDF. So if I go back over here, pretend that this is a CDF. So it looks kind of like a CDF. Okay, again, this is now our cumulative density function of our variable x. It goes from 0 to 1 over the domain of x. You'll notice that this is an invertible function, right? There's a 1-to-1 mapping between the value of our parameter and the value of the CDF. which means that we can calculate the inverse of the CDF, which basically tells us what value of our parameter encloses some percentage of the probability. And so the inverse of the CDF is called the PPF, the percentage point function. It's also sometimes called the quantile function. And so really the sigma problem is just calculate the PPF of a unit Gaussian at your p-value divided by 2, because again, a Gaussian is symmetric, and so you need to leave half of the probability on either side. And so basically this tells us that for our calculated p-value in this problem, the significance of using the textbook as a good study tool is 2.75 sigma. So it seemed very significant initially, but by modern physics and astronomy standards, maybe this isn't the most significant. Okay, so far we've looked at examples where we only have one data point, which is not going to be the case for basically every single application of Bayesian inference that you are going to encounter in your lives as astronomers. So now let's instead look at a kind of data set that should be more familiar to many of you, which is a time series. So some value as a function of time. And in this case, we're going to go back to analyzing linear signals. So first we're going to define our model. It's just y equals mx plus b, except I've called b c for constant. Okay, and we're actually just going to simulate the data ourselves. So we're assuming a time series where our sampling frequency is 10 hertz. So in 1 second of data, we have 10 data points. We have 10 seconds of data. So in total, we're going to have 100 data points. And we've chosen some true values of our linear parameters, a slope of 0.5 and an offset of 0.2. So we've generated our array of times, and then we're going to calculate our data, which is just our linear signal, plus some Gaussian noise. And in this case, we're going to assume white Gaussian noise, so sigma is independent of time, which basically allows us to say that, a measurement of this data set at one time is going to be independent of a measurement at another time. That's what white noise means, basically. And so we use NumPy to generate some random Gaussian noise. And if we plot this data, this is what it looks like. So we can see there's a linear signal in this data, and there's some noise that we know is Gaussian distributed. Okay, but let's assume that we didn't know how this data was generated, and now we wanted to recover, again, the concept of the best fit parameters that describe our data. So how do we do this in a Bayesian way? It's very similar to maximizing the likelihood, but we're going to build it step by step. So we already saw this Gaussian likelihood earlier. It's the exact same likelihood. So the probability of observing any given data point at a specific time is Gaussian in the residual between the data and the model. So the difference between the data and the model is called the residual often. And in this case, our model is just linear. And we're, for the purposes of this demonstration, going to assume that we know the properties of our noise. And so we're going to fix sigma equals 1 in our inference. But you can also infer sigma simultaneously with your model properties, and you'll see an example of how to do that in some of the problem sets tomorrow. And Adam already told us that we can basically multiply the likelihoods for independent measurements in order to get the total likelihood. So now we basically just need to implement this. All right, so we've coded up our likelihood. And we want to calculate the posteriors on our model parameters, so our slope and our intercept. So again, for simplicity, we're going to assume uniform priors on our parameters, and we're going to do this on a grid. So later on in the week, you're going to see how to use stochastic samplers to basically generate samples from the posterior, and that's in most cases that you will encounter in your actual research what you're going to do, because we suffer from the curse of dimensionality, right? So as you increase the dimensionality of your model, it basically becomes computationally intractable to calculate what is the probability as a function of the parameters of the model if the number of free parameters is more than like 3. So you don't want to calculate the probability on a 17-dimensional grid, which is often the number of parameters used for my preferred application of Bayesian inference and gravitational wave astronomy. But for us, we only have 2 parameters, and we haven't talked about stochastic sampling yet. So we're just going to do this on a grid, and this is not super computationally expensive, but we'll see tomorrow how we're going to increase the dimensionality by 1. So going from 2 to 3, you'll notice that the computation does actually get quite a bit slower. Okay, so we're going to choose some prior ranges for our parameters for the slope and the intercept. And then for a uniform prior, how do we calculate the prior probability density? Well, we know that the prior has to integrate to 1. So between our prior bounds at x1 and x2, this area under the curve has to be 1. So P of x is just 1 minus x2 minus x1, and it is constant across the entire domain of the prior by definition. All right, so we've calculated our priors, and then we can calculate our likelihood. So since we're doing this on a grid, we're just going to do it in a loop. We're calculating this over all the points on the grid. All right, now again, we need to calculate our posterior. So we do that by multiplying our likelihood by our 2 priors. And then we need to calculate the evidence. So in this case, since we now have continuous probability distribution over 2 parameters, our probability of the data, which is again just our evidence, is the integral of the likelihood. These are 2 priors. Okay. So again, this is why we call it the marginalized likelihood, because we've taken our likelihood and multiplied it by the priors on the parameters of our model, and we've integrated them out. So you can see that basically we've removed the condition on these parameters because we've done the integration. This is what it means to marginalize a parameter out of a distribution. And in this case, we've marginalized all the parameters of the model. You don't need to marginalize all the parameters of the model, and we'll see what that looks like in a couple slides. Okay, does the marginalized likelihood process make sense? Okay, great. All right, so we're also interested in calculating the 1-dimensional posteriors on the 2 parameters of our model. And to do that, we're just going to only marginalize 1 parameter at a time. So we're going to take our posterior on both parameters and basically just integrate out one of them. And you'll notice that in this case, I'm working with the posterior, but you could switch in the likelihood from Bayes' rule, right? So here we want the marginalized posterior on M, but if we wanted the marginalized likelihood, we would just swap this out with the likelihood times the prior on C. And we do the same, so we integrate 1 at a time, and that gives us the 1-dimensional probability distributions. And again, we integrate numerically. Okay, so we have all the elements of our puzzle. Now we want to see what our probability distributions look like and basically see if we've gotten the right answer, if we've recovered the parameters that we use to simulate our data. And so in order to do this, we're going to make what's called a corner plot. So this is often how we visualize multidimensional posteriors, and it's called a corner plot because you have a grid of n by n individual panels on a plot where n is the number of free parameters in your model. So for us, it's going to be a 2x2 grid. And the diagonal elements of the grid are going to show the one-dimensional marginalized posterior distributions that we just calculated, so P of M and P of C. And then all the other panels below the diagonal are just going to show the 2D posterior for a given pair of parameters. So in this case, we're only going to have one off-diagonal element because we only have two free parameters. And how you visualize that 2D posterior is up to you. A popular choice is to plot the 50 and 90% 2D like credible regions. So in 2 dimensions, what is the ellipsoid or blob of probability that encloses 50% and 90% of the total probability? And just gonna jump and show you what this looks like. So this is our one-dimensional posterior on the intercept in our data. So the orange line shows the true value. So we got it right. It's not exactly peaking in the right place, which we expect because we had some noise in our data, right? So the noise creates some random variability. And then this is our marginalized posterior on M, and you can see our two-dimensional credible regions, and you'll notice that P and M are correlated with each other, which makes sense. You can get very similar looking lines by either changing your slope or your offset. And so it's actually a good thing that we've measured these two parameters simultaneously because there are interparameter correlations. And so you can dig into the code for how we calculated the 2D probability region in the problems because you'll come back to doing this, but I want to leave some time for questions as well. Yeah, Megan. Okay. I thought there were two groups, each consisting of 20 students out of a total of 40. The group that read the textbook got an average grade of 16 out of 20. Okay, so I think there's some confusion here. There were two groups initially. In the class of 40 students, half read the textbook and half didn't. Of the half that read the textbook, 16 out of 20 passed the exam. So this is a very rudimentary exam. It's just pass fail. There are no grades. It's either pass or it's fail. And this is why we can model it as a Bernoulli process. And then the group that didn't read the textbook, 4 out of the 20 passed. And so then when we actually went to calculate our p-values, we kind of threw away the part of the class that failed the exam, and we only focused on the part of the class that passed the exam. And so then it became a problem of everyone in this group of 20 students has passed the exam. And then the two possible outcomes are they either did or did not read the textbook. I think that should help clarify the question. Other questions? All right, we have some extra time, so I'm going to go through in a little bit more detail how we actually calculate our 50 and 90% credibility regions on that 2D plot, because you guys are going to go and do this in the problem set. So for me, it's easier to think about how this is implemented in code, and so I'm basically just going to walk through each line of this. So the components that we need to calculate this are our two-dimensional array of posterior probabilities, which in this function I've just called fx. And then we have our grid spacing in our x dimension and our y dimension. So we have our two dimensions. Okay, and originally our posterior is a two-dimensional array. So first I'm just going to flatten it. And then I'm going to sort that flattened array by, well, in the next two lines by decreasing probability. And then I'm going to calculate my CDF, and this is kind of a weird CDF because it's technically over a two-dimensional array, but since we want our two-dimensional regions, this is what we need to do. And again, it's a CDF, so the maximum of the CDF can only be 1, so we're going to normalize it. And then basically we're just going to go and calculate that inverse CDF. So we want to find the point in the posterior where the CDF is equal to 0.5 and 0.9 because we want our 50 and 90% credibility regions. And then we also want our maximum posterior, and this is just the first element of our sorted posterior array. So this basically allows us to tell matplotlib, plot these contours when we pass it to contour F. So this is just what matplotlib needs in order to visualize this. And I will say that because we've done this on a grid, I've shown you how to make the corner plot by hand, but in reality, when you use a stochastic sampler, there are a lot of off-the-shelf Python packages that have really nice tools for making corner plots like Corner and Seaborn. And so like part of this was to understand what are the elements that go into a corner plot before you just tell like corner.corner plot my, NumPy array. But now hopefully you have some conceptual understanding of what are each of the panels showing. And if there are no other questions, we can go to the problems. So there are two problems. The first one is a classic application of Bayesian inference where we're looking at the accuracy of viral test results. So pretend a new viral pandemic has broken out and then basically calculate how likely you are to be sick if you've tested positive or not. And then I already alluded to the second problem. We're going to look at changing the prior for our textbook example. And then we're going to calculate credible intervals. So feel free to get started. And yeah, so basically you shouldn't need to use anything besides SciPy, NumPy, and Matplotlib for these problems. And the Jupyter notebook for this is uploaded into the day one folder on the drive. So you can see basically all the code that I use to go through these examples, and that'll be helpful for solving the problems.